All right. Hey, everybody. Welcome back. So in this next activity sheet 8, we are going to change gears from what we've been doing so far in the semester. So far, we've been looking a lot at integration strategies and other topics that include specifically the act of integration, typically in finding antiderivatives. We've learned a bunch of different techniques and strategies for doing this, and it's been good fun. This activity sheet and the ones that will follow after pivot a little bit and try to ask the question, now that we have all of these different ways to integrate, how, or maybe I should say what can we do with these? So what kind of questions can we answer using integration? Put another way, we're going to learn about different applications that we can use integration to answer questions about. And this first one is about finding the area between two curves or between two functions. So let's go ahead and get started. In the example that we're going to be looking at, we have two functions. One of them is given by f of x equals this thing right here, 5 minus, in parentheses, x minus 1 squared. And the other function is g of x equals 4 minus x. Very briefly, I'll try to sketch this quickly. There's a better picture further down, but I will say that one of these functions, the f of x, kind of looks like this, while the g of x, so that's f, the g of x kind of looks like this. Where the goal here is that we want to have our intercepts somewhat correct and somewhat realistic. So let's pretend it sort of looks like this. Okay, great. Two functions, and as we can see, each of these functions is a curve, and we can consider the area of curve that is intersected between them. In this case, notice that's going to be this section right up here. So our goal is to try to figure out what that area is, how much area is hidden between these two curves. And it turns out we can use integration to do this in sort of a clever way. Our first goal is to try to use algebra to find the points where f and g intersect, right? And so those intersection points, those are going to be these points here and here. So of course, these should be equal to each other in terms of their height, where the height of the function f of x is equal to the height of the function g of x. In other words, we're going to try to set f of x equal to g of x, and then we're going to solve for x. So we'll see which x values allow for these two to be equal to each other. So we've got a little bit of algebra here. I'm going to go ahead and pause the recording as we write some of this down. All right, so now we've gone ahead and solved this out. We see that it simplifies down to the equation negative x squared plus 3x equals 0. And I wanted to bring you back here for this final step, right? This means that we can factor out an x, so we get let's factor out a negative x times x minus 3 equals 0. And that just means that x will equal 0 and x will equal 3. And so again, those are the two x values. Let's say x equals 0 and 3. Those are the two x values that correspond to the points where f and g intersect, right? So here, of course, is x equals 0. And over here, that point, that should be x equals 3. Scrolling down, let's try that one more time. All right, there we go. Scrolling down, we're still interested in figuring out that blue area, which corresponds in the picture down here to this, sort of gray shaded area. So we're still sort of interested in this. And it turns out one way that we can do this is by trying to figure out some other shaded areas first. So here we have the picture of the two functions, sort of separate from each other, f and g. The shaded area represents the definite integral of each from x equals 0 to x equals 3. So over here, we see that the shaded area in that left-hand picture represents, what is that? That's going to be the integral from 0 to 3. of the function f of x dx. So again, that was 5 minus quantity x minus 1 squared. While over here, the purple region, that represents the integral from 0 to 3 of g of x squared. So that was just 4 minus x. All right, and what we can do is we can actually calculate each of these areas separately. I'm going to pause the video and do that now. All right, so what we see here is we've gone ahead and computed these. For the one on the left, I went ahead and computed that integral first by FOILing out the x minus 1 squared, distributing that minus sign, actually getting exactly the same thing that we had up here, and then just integrating that out by hand. I went ahead and hid the details, but the end result that we get, which you can quickly verify, is that we got 12 as our area. The picture on the right, again, you could compute the integral. Instead, I actually just noticed that this is a trapezoid, and I went ahead and used our good old formula for area of a trapezoid from way back in geometry. And again, we realized that this is 7.5. So we have our two integrals, but that doesn't directly answer the question that we're most interested in, the area of the curve between f and g. And here is where the wonderful additive nature or subtractive nature of area comes in, right? This area here is really nothing more than the original red area, which I'll go ahead and sketch in here, right? So original red area was all of this good stuff minus that sort of blue-purple area, which I probably chose a pretty bad color here because they look almost identical. But here's my purple area that I'm trying to subtract off. And isn't that just the worst, smudgiest picture that you've ever seen? But the idea here is that we should be able to calculate the area that we're most interested in by calculating that red area, that's 12, and then subtracting off that purple area, which is 7.5. So of course, this gives us 12 minus 7.5 is going to be, what is that, 4.5? This will be 4.5 as our final area. But I also want to highlight how we can figure out what this area is in a more, integrally kind of way. The 12, of course, was the integral of, that came from calculating the integral from 0 to 3 of f of x. And the 7.5, that came from calculating, again, we looked at a trapezoid, but it's the same thing as the integral from 0 to 3 of g of x dx. And so getting our answer here of the area between the two curves is nothing more than the one integral minus the other. And because integrals behave so nicely across, I should say, subtraction occurs so nicely across integration, this is nothing more than the integral from 0 to 3 of the function f of x minus g of x, treated as its own function in its own right, dx. And this gives us a framework to use integration as a method of finding area, not just signed area under a curve, but our usual direct definite integral. But this lets us set up an appropriate integral that lets us find the area between two curves. Thanks so much for watching, and we'll see you next time.